Welcome to the IMC Famos tutorial. In today's session, I would like to show you how you can calculate measurement uncertainty in IMC Famos and how you can benefit from this information. As you can see, I've already opened the IMC Famos software, and under Variables, there's the data set labeled Temperature. If I now right-click on the temperature label and then click on Show, a pop-up window opens displaying the data set. As you can see, the curve window displays the temperature measurement over time. To be able to visualize the data more clearly, we can click on the Show Grid icon. One can see that the temperature measurement is approximately 50 seconds long, and during the testing, a temperature increase occurs from approximately 24 to 36 degrees. Now I'd like to calculate the temperature rise time during the test. For this, I've prepared the following calculations. In order to calculate a rise time, or for that matter, any general calculation, you must select a function and a variable. As you can see here, for the data set temperature, we have selected the functions mean and cut to find the average temperature between the times of 5 and 10 seconds. Similarly, we also use the same functions to find the average temperature between 30 and 35 seconds. This represents the lower and upper levels of the data set. Now to calculate the rise time, we use the help variables L1 and L2. By clicking on Run Sequence, the functions are executed and the results for all three appear in the Variables window. As you can see, the results show a rise time of 8.6 seconds. If we once again look at the graphical display of the data set, the results appear plausible. As you can see, the rise starts at about 12 seconds and ends around 22. But how precise are these results? To estimate the uncertainty of the measurement, we need to take a look at the existing noise band. In the curve window, we can easily zoom in on a specific section of the line. If we look at the values, we can see that the peak-to-peak values are in the 1 degree Celsius range. Thus, we can estimate the measurement uncertainty to be about 0.25 degrees Celsius. Now, if we click on the second tab here, you can see that we have created some additional functions for calculating the uncertainty in the measurement. As you can see here with the function uncertainty set, you can add the estimated uncertainty to the temperature data set. The uncertainty loop function will perform 1,000 Monte Carlo experiments by adding slightly different values to the temperature data set. This is done by the function uncertainty modify. The next three lines are the same that we used in the first example. Then we calculate the uncertainty of the rise time by using the uncertainty calc function. The final function, uncertainty get, will display the results in the variables window. Now we can click Run Sequence to get the results. For a value of 8.6, we can see that we end up with an uncertainty value of 2.7, which means a relative measurement uncertainty of 30%. The correct interpretation of this result means that if you were to repeat the measurement several times, the rise time would be distributed around 2.7 seconds, and this level of uncertainty is not satisfactory. So what is the reason for this large uncertainty? Is the uncertainty of the temperature data set too large, or is it the algorithm that is bad? The answer is both. It is quite hard to change the uncertainty of the temperature signal because in order to do this, one would have to repeat the measurement, which is perhaps not possible. Or if it were possible, then it could be quite expensive because you may need a better test setup with better amplifiers or better sensors or so on. The algorithm, on the other hand, can be changed with much less effort. To do this, we simply add a smoothing function to the algorithm. After adding the smoothing function, we can once again click on the Run Sequence and the results appear in the Variables window. As you can see, the measurement uncertainty is now at 0.06 seconds. This means a relative measurement uncertainty of 0.8%, and in this case, that is completely acceptable. This example shows how you can easily estimate the uncertainty of your results using IMC Famos. Through the calculation of the measurement uncertainty of your results, you can qualitatively evaluate the changes in your algorithm, thus optimizing them and making them more robust. If you would like more information on the topic of measurement uncertainty, you can visit the white paper section on our website. Thanks for your attention, and stay tuned for the next IMC Famos tutorial.